Welcome to this video session. My name is Samuel Chukwuemeka. Happy New Year. In this video session, we shall discuss matrices. This is a long topic that we do in finite mathematics. Some also do it in discrete math, and some other topics for liberal arts majors and other majors as well. The applications, why are we learning this? Why are we learning matrices? The applications are so numerous. For companies that deal with a lot of production, that ship products, that it involves a large amount of data. So companies that produce products, like let's say a company that makes cars, and they ship it to various parts of the country or to various countries in the world, they need to organize their data. So they can use matrices to organize their data. Another application, matrices can also be used to design computer games graphics. Like, some of the games you do, or some of the puzzles or computer games that you do, that is like square matrices, 2 by 2 cubes or 3 by 3 cubes. Those are matrices. You can also use it to design the graphics of computer games, like your Xbox, okay, and so on. Now, you can also use matrices to describe the quantum mechanics of atomic structures. So these are several uses. These are part of the uses of matrices. That's why we are studying it. Now, when we go further into this topic, we deal with, other topics like the simplex method, maximization, minimization problems, and the rest of them. Okay, now, what is a matrix? Matrix is singular. This is singular, and matrices is plural. So what is a matrix? Matrix is a Latin word for womb. Womb. A womb contains, the child. It contains something that, something containing something. So we say that matrix it contains something, okay? Is defined as an ordered rectangular array of numbers. So it is an ordered rectangular array of numbers. It is ordered. It is a rectangular array of numbers. And it wasn't be numbers, okay? It could also be variables as well. It mustn't just be numbers. It could be variables as well. So that is what we mean by matrix. Okay? That's what a matrix is. Now, before we go further into this, we have talked about the uses, and I just defined it. We would look at briefly, we will look briefly on the mathematicians that contributed to this topic of matrices. The idea of matrix actually was first used to solve simultaneous equations, simultaneous linear equations. That was like the 3 by 2, the 2 by 2, the 3 by 3, 4 by 4, and the rest of them. So that was the first use of matrices. Okay, and the Chinese mathematicians were the first actually who noted this in their papers. And this guy commented on it, Liu Hui. I'm not sure I'm pronouncing the name right. Then we also have some other mathematicians that did some work on this, like Isaac Newton. We also have Seki, Kowa, that's the Japanese. Okay? We also have a Gottfried Leibniz. This mathematician also did work in calculus. Gottfried Leibniz. Then of course we have the popular guy here, Carl Friedrich Gauss. Gauss's law. Of course he is a popular mathematician. You see the Gaussian elimination method used for solving simultaneous linear equations. Or some textbooks will call it the Gauss's Jordan method. Carl Gauss. Okay? And you also see Gauss's law in electric circuits. Okay, you also have a Jordan, of course. Jordan, the Gauss's Jordan method. And then you have this female mathematician, Olga Taussky-Todd. This lady used matrices to analyze the vibrations on airplanes during World War II. During World War II, she's a female mathematician. She used matrices to analyze vibrations on airplanes during the Second World War. Okay? So there are several mathematicians that did some work, and these are some of them. And then you also have who? Samuel Chukwuemeka. Don't mind me, I'm just messing with you. Don't mind me. Anyway, okay, just put some smile on your face, okay? But anyway, that's by the way. I'm doing a little bit of work on this, on matrices, to see whether I can find something so that my name can be included. Anyway, so these are, we've defined matrices, we've talked about the uses. It's used to solve simultaneous linear equations. It is used for designing computer games graphics. It is used for organizing data for companies' products of companies. It is used for describing the quantum mechanics atomic structure. Okay? Quantum mechanics of atomic structures. Okay? And so much more. We have so many applications of matrices. Now, the next thing we're going to do now is we want to now do representation of matrices. How do we represent matrices? So we see that a matrix is represented, a matrix is represented as, we kind of represent it as a bold letter. Let's say A is matrix, and then A11, A12, A21, A22. So what does this mean? We represent a matrix as an uppercase letter, an uppercase alphabet, like you see A. Right? So a matrix is represented by an uppercase letter. Say A, uppercase A. That's how we represent matrices. B, C, D, E, F. Okay? Uppercase. Now, the elements of a matrix are represented by lowercase. The elements or entries, we call it elements or the entries. Remember, we said that a matrix is an ordered rectangular array of numbers or variables. So this is a rectangular array and it's ordered. The elements are called the entries. They are represented by lowercase letters with subscripts. lowercase letters with subscripts. You know what I mean by subscripts? 1, 1, 1, 2, 2, 1, 2, 2. Okay? So it's like the elements are A, I, J. A, lowercase, I, J. Okay? I, J are the subscripts. So this means element in the ith row and jth column. Element in the ith row and jth column. That's what it means. Okay? Element in the ith row and jth column. That is what it means. So when we have A11, what does it mean? A11 means element in the first row. You know what? Let me use first row and first column. First column. So that's what A11 means. So this tells you that this element is in the first row, first column. A12, what does it mean? A12, that means A subscript 1, 2 means element in the first row and second column. So that's the way you do it. Okay? This is the, look at what I mean here. I'm going to use this. Now this is the first row. Okay? The rows are the horizontal. The horizontal are the rows. Okay? This is the horizontal lines are the rows. Okay? And then this is the second row. Horizontal lines are the rows. And then the vertical lines are the columns. This is the first column. And this is the second column. So you should know this very well, you know, how we represent matrices. The matrix is represented by an uppercase letter, and then its elements are represented by lowercase letters with subscripts. So this is element in the first row, first column, that's A11. A12 means element in the first row and second column. A21 means element in the second row and first column. And A22 means element in the second row and second column. This is what it means. And then we now say that the size of the matrix, we call it size or dimension or order. Okay? We now say that the size, or you can say dimension, or order of a matrix. Okay? The size of a matrix, or the dimension of a matrix, or the order of a matrix is written as m by n. M by n. You see, I'm using the blue marker for the row, and I'm using the green marker for the column. So it's written as m by n, okay, which means row by column. We pronounce it as row by column. Row by column. So this will be row, how many rows by how many columns. Now, the x you see there times, we call it by. You can say m by n, or m times n. That's the way we write it. So let's look at this now, you see. Like this now, how many rows does this have? It has 2 rows and 2 columns. So because it has 2 rows and 2 columns, the size is 2 by 2. It's a 2 by 2 matrix. 2 by 2 matrix. Remember, it is row by column. Row are the horizontal lines and column are the vertical lines. Row by column. That is what we mean by the size of a matrix. Okay, let's kind of look at more examples. Remember, that is the size or the dimension or the order of a matrix. So if I write maybe that matrix, let me say matrices, maybe P is equal to minus 2 minus 4, K is equal to minus 1 minus 3 minus 5, 2, 4 minus 1. Okay? G is equal to 1, 0, 5 minus 1, 0, 2, 2, 1, 1. So what is the size? What is the order of these matrices? What is the order of these matrices? Okay, this one, how many rows? We have first row, second row. Okay, this is the first row, -2, and this is the second row, -4. So it has 2 rows. And how many columns? It just has 1 column. So this is a 2 by 1. 2 by 1. 2 by 1 matrix. Has 2 rows and 1 column. I'm using 3 markers. This is like blue is the rows and green are the columns. Now, you can also write it as this. You can also write it as 2. You can also say 2 by 1 matrix. 2 by 1 matrix. Because it has 2 rows. It has P11 and P21. Okay, P11, in this case, P11 is what? P11 is -2, and then P21 is -4. So it has 2 rows, but only 1 column. This is the first row, this one is the first row, and this is the second row, and that is just 1 column. Okay, here, yeah, I probably will just write with black so that I save time. Here, K, what is K here? How many rows? This is first row, second row, and this is first column, second column, third column. Okay? This is first row, second row, right? And then this is first column, second column, third column. So K is what? Is a 2 by what? 2 by 3 matrix. 2 by 3 matrix. 2 rows and 3 columns. So K11 is -1, K12 is -3, K13 is -5, K21 is 2, K22 is 4, and K23 is -1. Please take note of how you take the elements. Okay, K23, small k subscript 23 is -1. 2 by 3 matrix. Okay, G. How many rows? First row, second row, third row. How many columns? First column, second column, third column. So this is what? 3 by 3 matrix. 3 by 3 matrix. Remember, you can also write it as this. You can also write it like this, 3 by 3 matrix. Okay? G11 is 1. G12 is 0. G13 is 5. G21 is -1. G22 is 0. G23 is 2. G31 is 2. G32 is 1. G33 is 1. Okay? Now I've got to exercise because, so that I don't, it's a cold weather, so I want to exercise. Anyway, I hope you smiled at that. Okay. So, this is how we note the order of matrices. Okay? Or the size of the matrix or the dimension of the matrix. Alright, now the next thing we shall talk about, now this is matrices part 1. This is just the beginning. I'm not going to do everything about matrices tonight. So you can watch out for other videos. Let me write this matrices part 1. Okay. Now, the next thing we want to talk about now is the types of matrices that we have. Okay? Types of matrices that we have. Types of matrices. Now, there are so many types of matrices. And the list is not exhaustive. We will just talk about some of it in this video because this is just the first part and we're looking at time. As we do more work on matrices, we shall find other types as well. So let's start with the first one. We have what we call a row matrix. Now, some textbooks call it row vector. Some textbooks will call it a row vector. Okay? This is a matrix that has only one row. A matrix with only one row. A matrix with only one row. It could be any number of columns, it doesn't matter. Okay, the main thing is that it has one row. Okay, so it could be like this. Examples. It could be like this. 1. It could be 1, 2. It could be 1, 2, 3. It could be -1, 0, 1, 4. Okay? Now this is 1 by 1. 1 row and 1 column. This is what? 1 by 2. 1 row and 2 columns. This is 1 by 3. 1 row, 3 columns. This is 1 by 4. 1 row, 4 columns. So whatever how many columns it has, we don't mind. We don't care about that. The main thing is that it has just one row. That means it's a row vector or a row matrix. Number 2, we have what we call a column matrix. Column matrix or a column vector. Now, this, of course, you are already from the idea. Row matrix has only one row. So, what is a column matrix? It has only what? One column. So, it's a matrix with only one column. A matrix with only one column. Okay? So, no matter what it does, it has one column. Examples, we can have this. We can have this, 1, 2. We can have this, 1, 2, 3. We can have this, -1, 0, 1, 4. So these are all column matrices. These are all column matrices. Okay? This has this 1 by 1. This is 2 by 1. 2 by 1. This is 3 by 1. This is 4 by 1. They're all column matrices. All right. 3. We have what we call zero or null matrix. Zero or null matrix. This is a matrix whose elements are zeros. Elements or entries. A matrix whose elements are zeros is what we call a zero matrix or a null matrix. Okay? For example, we can have examples. We can have 0, 0, 0, 0. Okay, we can have 0, 0, 0, 0, 0, 0. Okay, this is a 2 by 2 0 matrix, and this is a 2 by 3 0 matrix. 2 by 2 0 matrix, 2 by 3 0 matrix. Or 2 by 2 null matrix, 2 by 3 null matrix. Okay, the next one, number 4, we have what we call square. Well, before we go to square, let's look at rectangular matrix. Rectangular matrix. This is a matrix that, that does not have an equal number of rows and columns. Okay, it's a matrix that does not have an equal number of rows and columns. It has an unequal number of rows and columns. We call it a rectangular matrix. Example, 1 by 2, 2 by 1, 3 by 4, 2 by 5, okay? 1 by 2 will be 1 row and 2 columns. Maybe -1, 2. I'm sorry, this is a 2 by 1. 1 by 2 will be -1, 2. Okay, 1 by 2, 2 by 1, 2 by 3 will be 2 rows and 3 columns. 2, 1, 5, -1, 4, 6. 2 by 3, it doesn't have equal number of rows and columns. You can have a 4 by 5, 4 rows and 5 columns. Let's see how it looks. 1, 3, 2, 4, -1. 1, 2, 3, 4, -1. Then 2, 1, 2 minus 1 minus 3, 4, -2. Remember, it has 4 rows and 5 columns. 0, 0, 1, 5, -6. 1, 1, 2, 3, 7. 4 rows, 5 columns. 4 by 5. 4 by 5 matrix. Okay, and the rest of them. Now, this is what we know as rectangular matrix. The next one, number 5. We have what we call square matrix. Square matrix. Square matrix is a matrix with an equal number of rows and columns. It's a matrix that has an equal number of rows and columns. Okay? For example, we are looking at examples. We have 2 by 2, 2, 4, -1, 2. We have 3 by 3, 1, 4, -1, -2, -5, -8, 1, 6, 1. 3 by 3, we have 4 by 4, -1, 4, 6, 2, 2 minus 1, 4, 5, 0, -1, 2, 0, 5, 1, 3, 5. 4 by 4, 5 by 5, 6 by 6 is what we call a square matrix. Okay, next one. We have a diagonal matrix. Diagonal matrix. A diagonal matrix is a matrix, first of all, a diagonal matrix is a square matrix. okay, is a square matrix first, whose diagonal elements, first of all, the diagonal elements, what are diagonal elements? The diagonal elements are the elements along the principal diagonal. This is what we call the principal diagonal of the matrix here. It goes this way, not this way, but this way. Okay? This is what we call the principal diagonal of the matrix. And the diagonal elements are 2 and 2. This one is what we call the principal diagonal of the matrix. The diagonal elements are 1, -5, and 1. This is what we call the principal diagonal of the matrix. The principal diagonal goes like this, not the other way around, just like this. And the diagonal elements here are -1, -1, 2, and 5. So a diagonal matrix is a matrix whose diagonal elements, the diagonal elements are elements along the principal diagonal, of the matrix. Okay, what I just showed you is what elements along the principal diagonal are non-zeros, and then all other elements are zeros. Then all other elements or entries are zeros. So that's what is a diagonal matrix. For instance, let's look at that. If you look at this one, the examples, you have 2, 2, 0, 0. Okay? Here you have, the next one, you have 1, 0, 0, 0, -5, 0, 1, 6, 0. I'm sorry, 0, -5, 0, yeah. Then 1, 0, 1. Okay? The elements along the principal diagonal are non-zeros. Then all other elements are zeros. This should be 0. Sorry. Yeah. All other elements are zeros. Then if we want to do it in this one it will be -1, 0, 0, 0. Then 0, -1, 0, 0. This will be 0, -1, 2, 0. And then this will be 0, 0, 0, 5. Okay, I made another mistake here. 0 here. Yeah, you just have to be careful, very careful. Okay, you just have to be careful. And you want to probably look at it again so you make sure you got it right. If you are trying to convert that to a diagonal matrix. So the diagonal matrix, like we said, the elements along the principal diagonal are non-zeros and all other elements are zeros. That's what we call a diagonal matrix. Now, for this particular one, if you look at this particular one, you see that this is 2, 2. They are the same. We have a special type of diagonal matrix such that the diagonal elements are equal. Okay? Such that the diagonal elements are equal. That is what we call a scalar matrix. That's the next thing we'll talk about. So as you can see, you see that all diagonal matrices are square matrices, right? But not all square matrices are diagonal matrices. But all diagonal matrices are square matrices, must. Okay? Now the next one we have is scalar matrix. Scalar matrix. Now, of course, the scalar matrix is is a special type of diagonal matrix. This is a diagonal matrix, but the diagonal elements are now equal. They are now equal. Remember, they are non-zeros now. They are non-zeros. Diagonal elements must be non-zeros. And every other element, all other elements are zeros. Yeah. But when you now have it that the diagonal element is of course, is a diagonal matrix in which the diagonal elements are equal. Okay, that's what we call a scalar matrix. Actually, this is a scalar matrix here. It's also a diagonal matrix, but it's also a scalar matrix. Okay? Examples. We have the 2, 0, 0, 2. That's a 2 by 2 scalar matrix, or 2 by 2 scalar diagonal matrix, 2 by 2 scalar diagonal square matrix. I mean, it's a diagonal matrix, is a square matrix. You also have another one. You can have a -3, 0, 0, 0, -3, 0, 0, 0, -3. This is also a scalar matrix because all these are equal. The diagonal elements are equal. That's what we know as a scalar matrix. Okay, so you see now that all scalar matrices are diagonal matrices, but not all diagonal matrices are scalar matrices. Right? Am I making any sense? Am I making any meaning? Does it make sense? I hope it does. Okay, the next one, identity matrix or unit matrix. Identity matrix or unit matrix. Now, this is a scalar matrix that has only diagonal elements as 1. Okay, you see how it flows. I started with, I wanted to deal with rectangular then because I now dealt with square because we have a lot with square. Okay, from square I went to diagonal, and then from diagonal I came to scalar. Now from scalar I'm going to identity matrix. It's represented by I, denoted by I, denoted by I, uppercase I. So anytime you see uppercase I, you know that it's an identity matrix. And this is very important. And when we do inverse of matrices, it's important. So what's an identity matrix? It's a diagonal matrix in which the diagonal elements are just 1. So you can also say that it's a scalar matrix, but the diagonal elements are 1. Yeah. But I would just prefer to say a diagonal matrix in which the diagonal elements are 1. Okay? It's a diagonal matrix. Of course, it's also a square matrix. In which the diagonal elements are 1. So you can have a 2 by 2 identity matrix. Examples, you can have 2 by 2 identity matrix. This is 1, 0, 0, 1. Identity matrix is very, very important. Very important. Okay? 1, 0, 0, 1. Some textbooks will write it as this. I, 2. I subscript 2. Or some textbooks will write it like this. I, 2 by 2. So whenever you see this, just know that some textbooks will write it I subscript 2, because we already know it's a 2 by 2 anyway. Or some textbooks will go ahead and write it I, uppercase I, subscript 2 by 2. And then of course 3 by 3 will be what? What will be 3 by 3? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? Identity matrix. Okay? Identity matrix. You know what? I will not have cleaned diagonal matrix because I'm still going to use it. This will be 3 by 3 identity matrix. 1 0 0 0 1 0 0 0 1. And then 4 by 4 will be 1 0 0 0 0. 4 by 4 will be what? 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. 4 by 4 identity matrix. Okay. Now number 9, we have what we now call triangular matrix. Triangular matrix. So you see, from square matrices we've achieved a lot of things. From square matrices we got diagonal. From diagonal we got scalar. From diagonal we got identity matrix. Now from diagonal again we're gonna get triangular matrix. From diagonal. Now what's a triangular matrix? A triangular matrix is, first of all, in this case we see, we look at a square matrix. Yeah, actually the triangular, we get it from square, I'm sorry. From the triangular matrix, we look at a square matrix first. It's going to be a square matrix. In this case, we the ones that are zeros, the elements that are zeros are either below the diagonal elements or above the diagonal elements. You know, kind of forms like a triangle. That's why we call it triangular matrix. First of all, we look at a square matrix, and then the below the diagonal elements will be 0, or above the diagonal element will be 0. Okay? It's a matrix. It's a square matrix, not just a matrix. A square matrix. It's a square matrix in which, okay, the elements below the diagonal elements are all zeros. Now, the diagonal elements are not zeros. The diagonal elements are not zeros, okay? But the elements above it are all zeros, or the elements below it. Now, if it is the elements above and below, then it becomes a diagonal matrix. Okay? If it is both above and below, then it becomes a diagonal matrix. But if one part below it is 0, okay, it becomes an upper triangular matrix. If above it is 0, it becomes a lower triangular matrix. So a triangular matrix is a square matrix in which either the elements above the diagonal elements are 0. Are zeros. Okay? In this case, we call it, in this case, it is called a lower triangular matrix. A lower triangular matrix. Lower triangular matrix. Okay? Or either, or the elements below it, or the elements below the diagonal elements are zeros. Now, you know what? I am going to put something here. Only either the elements above the diagonal elements are zeros only, okay? Or in this case, we call them a lower triangular matrix. Or the elements, either the elements above the diagonal elements are zeros only. In this case, we call it a lower triangular matrix. Or the elements below the diagonal elements are zeros only. Okay? In this case, it is called an upper triangular matrix. In this case, it is called an upper triangular matrix. Triangular matrix. Yeah. So look at what I mean here. I'm going to show you what I mean here. Look at what I mean here. When you have a square matrix, okay, let's say we have 2 by 2 square matrix, 2, -1, 4, 5. Okay, this is a 2 by 2 square matrix. 2 by 2 square matrix. If we have this, just pay attention. If we have 2, 0, 0, 5, are you with me? This will be 2 by 2 diagonal matrix. But if we have it like this, if we have 2, 0, 1, 5, okay? You see, this is the element above E. The element above E is 0. That means it will be what? 2 by 2 lower triangular matrix. Lower triangular matrix. Because the element above the principal the elements above the diagonal elements are the ones that are zeros only. And if we have it like this, 2, 0, 2, okay, by row, if we have it 2, -1, 0, 5, by row. Okay? This will be what? 2 by 2 upper triangular matrix. Upper triangular matrix. Okay, let's look at 3 by 3. Let's look at examples involving 3 by 3. If we have this, two, 5, 4, 1, 3, 2, -2, -2, -3. This is a 3 by 3 matrix, 3 by 3 square matrix. 3 rows and 3 columns. Okay? A11 is 2, A12 is 5, A13 is 4, A21 is 1, A22 is 3, A23 is 2, A31 is -2, A32 is -2, and A33 is -3. Okay, so this is a 3 by 3 square matrix. Now when we have it like this, 2, 0, 0, 0, 3, 0, 0, 0, -3. The diagonal elements are non-zeros. Every other guy is zeros. This is a 3 by 3 diagonal matrix. Okay? Now when we have it like this, 2 by column. Let me now read by column. I've been reading by row. Okay? Let me read by column. 2, 1, -2, 0, 3, -2, 0, 0, -3. I read by column. Okay? If we have it like this, this is the principal diagonal, 2, 3, -3. That are the diagonal elements, the principal diagonal. And all other zeros are above it. Okay? This is known as 3 by 3 lower triangular matrix. Okay? Now when we have it by this, when we have it like this, and I'm gonna read it by column, okay? If we have it like this, 2, 0, 0 by column, I'm reading by column now, not by row. 5, 3, 0, 4, 2, negative 3. Okay? You see that? Element below the elements below the principal diagonal, the diagonal elements are zeros. This is now 3 by 3 upper triangular matrix. Now let me kind of show you this, because if you look at this, assuming you come on this, if you kind of want to draw this as a triangle, right? Assuming you want to draw it like a triangle, looks like this, right? And if you want to draw it like a triangle, I mean, you can use this just to remember it.